Welcome to our presentation on Chapter 2, Data Preprocessing and Exploration, the second chapter of the data mining course. I am Dr. Roshdi Budjayam, Associate Professor at Galma University, and I will be your guide through this chapter. Today we'll explore one of the most critical steps in the data mining process. By the end of this presentation, you will be able to interpret exploratory data analysis results, use data preprocessing techniques to prepare datasets for mining, and examine patterns and relationships in complex datasets. Introduction. Raw data is often incomplete, noisy, and inconsistent, which can lead to misleading or incorrect conclusions. Data preprocessing is a critical step in the data mining process, as the quality of the data directly impacts the accuracy and reliability of the results. For example, if a dataset contains missing values for certain attributes, these values must be either filled in or removed to avoid biasing the results. Similarly, if the data contains outliers or errors, these must be addressed to ensure the accuracy of the analysis. Data types and formats. Before digging into data mining process and techniques, it is imperative to understand the different data types to be able to handle them correctly. Data comes in various types and formats, and understanding these types and formats is essential for effective preprocessing. The most common types of data include structured data, unstructured data, and semi-structured data. Let's take a closer look at each of these types. Structured data is organized in a tabular format, with rows representing records and columns representing attributes. This type of data is easy to analyze using traditional data mining techniques. Examples include relational databases, Excel spreadsheets, and CSV files. You can see an example of structured data represented in a table format with columns for name, price, and quantity, and rows that represent individual records. In the contrary, unstructured data does not have a predefined format. This could include audio, video, text, or images. Analyzing unstructured data requires specialized techniques such as natural language processing for text or computer vision for images. The third type is semi-structured data, which maintains some organization but does not follow the strict structure of traditional structured data. It is more adaptable and tolerant of different data formats because it does not have a set schema or data model. Examples include JSON, XML, and markup languages, which are commonly used in web applications. It can also include emails, configuration files, sensor data, machine logs, HTML web pages, social media posts, blockchain transactions, and more. Understanding the type and format of the data is crucial for selecting appropriate preprocessing techniques. For example, text data may require tokenization and stemming, while numerical data may require normalization or scaling. Data preprocessing process. After understanding the different types of data, we can move on to the data preprocessing process. This is a crucial step in the data mining process, as it prepares the data for analysis and ensures that it is clean, consistent, and suitable for mining. This stage plays a crucial role in enhancing the overall quality and reliability of the data. The preprocessing phase typically includes tasks such as handling missing values, removing noise, normalizing data, and selecting relevant features. The data preprocessing process involves four main stages: data cleaning, data integration, data transformation, and data reduction. The first stage is data cleaning, which is the process of detecting and correcting errors, inconsistencies, and inaccuracies in the data. This step is essential for ensuring the quality of the data and improving the accuracy of the analysis. Common data cleaning tasks include handling missing values, removing noise, and correcting inconsistencies. The first task in data cleaning is handling missing values. Missing values can significantly impact the results of data analysis and mining, leading to biased or incorrect conclusions. Missing values can occur due to data entry errors, sensor malfunctions, or other issues. Missing values can be represented in various ways, such as NaN, not a number, null, or empty strings, depending on the data type and format. In structured data, missing values may appear as blank cells in a table, while in unstructured data, they may be represented as missing text or incomplete records. In semi-structured data, missing values may be represented as null fields or missing attributes in JSON or XML documents. Handling missing values is a critical step in data cleaning, as it ensures that the dataset is complete and ready for analysis. Failure to address missing values can lead to biased results, as the analysis may be based on incomplete or inaccurate data. There are several strategies to handle missing values, including removing records with missing values if the number of such records is small, filling in missing values using statistical methods such as mean, median, or mode, and using advanced techniques such as imputation or predictive modeling to estimate missing values. Let's start with removing noise process. Noise refers to random errors or outliers in the data that can distort the analysis. Techniques for removing noise include smoothing, which is creating an approximating function that attempts to capture important patterns in the data while leaving out noise or other fine-scale structures, and outlier detection, which is the identification of rare items, events, or observations which deviate significantly from the majority of the data. Like noise, inconsistent data can arise due to differences in data entry formats, units of measurement, or coding schemes. For example, dates may be recorded in different formats such as day, month, year, versus month, day, year, or categorical variables may have inconsistent labels such as male versus M. These inconsistencies must be resolved to ensure the data is accurate and reliable. In addition to data cleaning, data integration is another way to handle missing values. It involves combining data from multiple sources into a unified dataset. This is often necessary when working with data from different departments, systems, or organizations. Common challenges in data integration include schema integration and entity resolution. Schema integration occurs when different datasets use different schemas or attribute names, making it difficult to combine them. Schema integration involves resolving these differences by mapping attributes and standardizing formats. Entity resolution involves identifying and merging records that refer to the same entity, such as the same customer or product, across different datasets. Techniques for entity resolution include record linkage and deduplication. Once the data is clean and integrated, it may need to be transformed into a suitable format for analysis. Common data transformation techniques include normalization, aggregation, and encoding categorical variables. Normalization involves scaling numerical data to a standard range, such as 0 to 1, to ensure that all attributes contribute equally to the analysis. Normalization is particularly important for algorithms that are sensitive to the scale of the data, such as k-means clustering or gradient descent. Aggregation involves summarizing data at a higher level of granularity, for example, calculating monthly sales from daily sales data. Aggregation can help to reduce the complexity of the data and highlight important trends. Encoding categorical variables is necessary because many data mining algorithms require numerical input, so categorical variables such as gender or product category must be encoded as numbers. Common encoding techniques include one-hot encoding and label encoding. For example, gender can be encoded as 0/1 instead of M/F, or height categories as 0/1/2 instead of tall, medium, short. The final stage of the data pre-processing process is data reduction. In this stage, data reduction techniques are used to reduce the size of the dataset while preserving its essential characteristics. This stage is crucial for improving the efficiency of the analysis by reducing the size of the dataset while retaining its essential characteristics. This is particularly important when working with large datasets, as it can significantly reduce the computational cost of the analysis. Common data reduction techniques include dimensionality reduction, sampling, and discretization. Dimensionality reduction involves reducing the number of attributes in the dataset by selecting the most relevant features or creating new features that capture the essential information. Techniques for dimensionality reduction include principal component analysis, PCA, and feature selection algorithms. Sampling involves selecting a subset of the data for analysis. Sampling can be random, such as selecting records at random, or stratified, such as ensuring that each subgroup in the data is represented proportionally. Discretization involves converting continuous numerical data into discrete intervals or categories. For example, age can be discretized into ranges such as 0 to 18, 19 to 35, and 36 to 50. Discretization can simplify the analysis and make it easier to interpret the results. Exploratory data analysis. Now that we have covered the data preprocessing process, let's move on to exploratory data analysis, EDA. EDA is a crucial step in the data mining process, as it helps to summarize and visualize the data to gain insights and identify patterns. EDA plays a vital role in determining the appropriate algorithms and techniques to be applied in the data mining process. Common EDA techniques include summary statistics, data visualization, and correlation analysis. Summary statistics involve calculating descriptive statistics such as the mean, the median, the standard deviation, or quartiles to summarize the data. Visualization is another powerful technique for exploring data using graphical representations such as histograms, scatterplots, and boxplots can help to identify trends, outliers, and relationships between variables. Visualization can be performed using various tools and libraries, such as Matplotlib, Seaborn, or Tableau. These tools allow users to create interactive and informative visualizations that can help to uncover patterns and insights in the data. The third technique is correlation analysis, which involves measuring the strength and direction of the relationship between variables. This can be done using correlation coefficients such as Pearson's or Spearman's rho. Correlation analysis can help to identify potential predictors for predictive modeling. In conclusion, data preprocessing and exploration are essential steps in the data mining process, as they ensure the quality and suitability of the data for analysis. By cleaning, transforming, and reducing the data, and by using exploratory techniques to gain insights, professionals can uncover meaningful patterns and build accurate models. Effective preprocessing and exploration lay the foundation for successful data mining and enable organizations to make data-driven decisions. Thank you for your attention.